Next up, we've got Julia. She's coming from Wisconsin. And by Rob.
Yes, hi. So I'm going to talk about some recent work that Rob and I did, which shows that sparsest solutions to neural network training problems for single hidden layer ReLU networks are provably recovered by an LP type of regularization with P between 0 and 1. So particularly, we're studying over-parameterized single hidden layer neural networks, ReLU networks. So that type of model can fit a given data set in many different ways. What we want to know is, are there any regularization strategies which are guaranteed to give you a sparsest solution? And there's different ways you can measure sparsity, but the one we look at here is a type of sparsity in the parameters is basically counting the number of non-zero entries of the input weight vectors that could or could not include the bias, depending on how you do it, of the active neurons, so the neurons that are actually contributing to the network output. And what we show is that by minimizing an LP path norm, which I'll say exactly what that is in a second, type of objective on the network parameters, for a sufficiently small p between 0 and 1, you're guaranteed to get an exact sparsest interpolating solution. To our knowledge, that is the first guarantee of exact sparse recovery that exists for ReLU neural networks with arbitrary data. And in the univariate case, so when you're fitting data points, which are just scalars, which are one-dimensional, you can also, our analysis also shows a little bit more. So you can explicitly characterize the functions that are learned when you solve this type of LP minimization problem, and that analysis gives you some bounds on the Lipschitz constant of the solutions, and in parametric terms of the neural network, it gives you bounds on the parameters and the width. So this idea of minimizing an LP quasi-norm for p less than 1 has been, in order to induce sparsity, has been studied pretty extensively in the context of compressed sensing for linear problems. So there the problem is like you have a matrix and a set of sort of Y, a set of labels, and then you want to find the vector with a minimum LP norm, which sort of solves that system of linear equations. And even in that case, where you're looking at a linear problem, it's not super trivial to actually prove that LP norm minimization will give you a sparsest solution. And those proofs don't really extend to neural networks very easily at all, because the problem with neural networks is very nonlinear, it's non-convex, it's sort of difficult to solve using those techniques. For neural networks, there are a lot of empirical sparsity promoting schemes that people have studied. They typically involve like some sort of elaborate like network parameter pruning type of schemes, but none of them really come with any guarantees that they're actually going to give you a sparsest solution. It's just all empirical. There are a few sort of specialized settings under which certain types of regularization are known to give you sparse solutions, but they typically require some fairly restrictive assumptions on the data, which our results do not require. So to go a little bit through the analysis in the univariate case, in this particular case, neural networks, single hidden layer ReLU networks are just functions of the form I wrote there. So they're linear combinations of ReLU neurons parameterized by input weights W, biases B, and output weights V. And in the univariate case, we include this extra additive term, which is a skip connection or residual connection. And we're comparing these two problems. So the problem we're looking at, problem P, minimizes what is basically an LP type of path norm on the parameters of the network. So it takes the product of the input and output weights for every neuron, takes absolute value, raises it to the pth power, and then sums it all up. So we want to minimize that objective subject to an interpolation constraint. And the limit of that objective as P goes down to 0 is just the count of which of those products are non-zero. So that's the same as counting which of the neurons in the network are active, or basically non-trivial. So the first thing we have is a theorem which says that there is some threshold, P star, which is data dependent, such that if P is smaller than that threshold, solving the first problem will always give you a solution to the second problem. Oh, and also solutions to the first problem are unique for all but finitely many P between 0 and 1. Okay, so how do we do this? Well, the basic idea is that neural networks are continuous piecewise linear functions. In the univariate input case, the kinks in the function, so the places where the slope changes, each kink corresponds to one neuron in the network, and the change in slope is given by the output weight of that corresponding neuron. So the LP path norm minimization problem is really just saying we want to find the continuous piecewise linear function which interpolates the data such that the sum of absolute slope changes, each to the pth power, is minimal. And for p equals 0, that's just saying we want to find the interpolant, but that has the fewest total number of kinks, so the fewest number of neurons. So when you're looking at it that way, one of our sort of intermediate result basically says that the solution to any solution to the minimum LP path norm problem, its behavior is sort of uniquely determined everywhere except when you have sequences of consecutive data points where the discrete curvature of the data is the same, by which I basically mean that the slopes of the straight lines connecting the data points are either monotonically increasing or decreasing. And it's on those types of regions when you have more than 3 data points in a row, which sort of have that constant curvature, that the solutions are a little bit harder to pin down. But what you can say for sure is that the sort of solution to the LP minimization problem, whatever it is, the concavity of that solution has to match the concavity of the data. And the number of knots of the solution on that interval is no greater than the sort of number of data points, which are like determining this sort of stretch of consecutive constant curvature data points. Once you realize that, you can sort of observe that the slopes of the neural network solution, the minimum LP solution, whatever they are, they have to be written as convex combinations of the sort of surrounding data slopes. And that allows you to rewrite the optimization as a minimization subject to a convex constraint set. And once you do that, then you're sort of back in the land of convex analysis, and you can use existing theorems about minimizers of concave functions over convex sets to sort of give you the sparse recovery result that we stated before. And from that characterization, you also get a few other things. So in particular, it tells you that every solution to the LP minimization problem for any p between 0 and 1 is a solution for p equals 1. So that basically tells you that there are solutions, which could be sparsest solutions, but which have really large steep slopes. So they look like the thing on the bottom right. It has the fewest possible number of kinks, but the slopes of the function itself are very large. And this tells you that that is not happening when you do LP minimization, that you're sort of getting an implicit L1 control on the magnitudes of the slopes. So that gives you like a Lipschitz bound on the actual learned function, and that corresponds to bounds on the network parameters. On the other hand, you can also have L1 solutions, which look like the thing on the bottom left, which they're solutions to the L1 path norm minimization problem, but they're infinitely non-sparse. They can look like the green, red, or blue things, which all have the same L1 path norm objective, but have sort of infinitely many teeny tiny little kinks. And that tells you that, or sort of our result tells you that that is not happening either for p between 0 and 1. That basically when you do p LP minimization for p between 0 and 1, you're getting the thing which is like the black spiky solution on the left. Its slopes aren't too big, but it's also sparse. Okay, and so some of this can be extended to neural networks with multidimensional inputs. So in this case, it's a little easier if you wrap biases into the input weights, but that's not necessary. You can do it without doing that. And then now, what we define as the LP path norm is, because the input weights are vectors instead of scalars, now we take the sum of LP norms to the pth power of each of these input-output weight products. And we look at minimizing that subject to interpolation and also subject to a boundedness constraint on the parameters, which I conjecture is necessary, but I'm not 100% sure. But if you look at these two problems, you can prove an analogous sparse recovery result, which is, again here, there's a threshold below which minimizing the LP problem is guaranteed to give you a solution to the L0 problem, a sparsest solution. And you can also extend this to, instead of just interpolation, to loss functions, sort of regularized loss functions, as long as the loss function is continuous piecewise linear in its second argument. You could maybe do other loss functions. You probably could too, but it would probably need like a different technique. But this exact argument works for like hinge loss, L1 loss, or L infinity loss as well. And the bird's eye view, what all this like nasty stuff says is, it's basically based on a paper from a few years ago by Mert Palanci, I don't know how it's pronounced, which shows that weight decay, neural network training problems with weight decay can be rewritten as sort of very large convex training problems subject to a linear constraint set. And that linear constraint set is sort of determined by looking at all the different ways that any set of ReLU neurons could like subdivide the data and sort of be active on some data points and not active on all other data points. And there's only finitely many ways that can happen. So here we use a very similar type of reformulation, but now it turns into a minimization of a concave function because the LP norm for p less than 1 is concave over this linear, this very sort of large but linear convex constraint set. Once you've reformulated it that way, you, again, are kind of back in the land of where convex analysis can tell you that solutions to that problem need to occur at the vertices of your constraint set, your linear constraint set. And because it's a finite dimensional linear constraint set, it's a polytope, so there are only finitely many sort of places a solution can occur. And once you know that, you can kind of use some like fairly standard norm inequalities to basically show this sparse recovery result that we stated. This multivariate analysis doesn't get you the functional characterization, though, that you get with the univariate problem. So it recovers the sparse, gives you the sparse recovery result, but it doesn't give you everything that you can also see in the univariate case. So basically, just to wrap everything up, this is, to our knowledge, again, the first sparse recovery kind of guarantee for ReLU neural networks with arbitrary data. The LP objective is also differentiable everywhere away from 0, so it could potentially be compatible with gradient descent, which kind of makes it maybe attractive for practical use. And it would be really great if we could extend this to deep networks, to other notions of sparsity, maybe other activation functions. Yes, those would all be interesting directions. And also look at algorithms that sort of implement this in the best performing possible way. Yeah.
Could you give some intuition for, like, you said that this optimal threshold P star is data dependent. Yeah. Like, what's driving this threshold towards 0? Like, in the univariate case, you mentioned these regions of constant discrete curvature, yeah. And I think like bigger regions means P star needs to be smaller.
Yeah, if those regions are small, then that P star threshold is just equal to 1. So it's very easy to say what it is if you don't have any of those regions, or if there's no more than like 3 of those consecutive regions. Bigger than that, in all the cases I could find, the slopes have to be very, very extreme in order, like the data has to sort of be very, contain in itself very extreme slopes in order for that P star threshold to not be 1. Like in most practical scenarios, I think it's just 1, but sometimes for really extreme slopes, you can design scenarios, like for very extreme kind of data sets, you can design scenarios where it's not 1. But the thing that's pushing it to sometimes not be 1, for you to have to get P closer and closer to 0 is the extreme sort of slope changes that are in the data set itself.